Welcome to this deep tech briefing. Today, we're mapping out the physical, economic, and thermodynamic realities that are literally dictating the future of artificial intelligence. Because, if you really want to understand where AI is heading, you can't just look at the software. You have to look at the silicon. So let's dive right in.
Here is our roadmap for today. We'll be hitting 6 key areas: the nanoscale foundations of compute, AI's hardware symbiosis, advanced packaging, geopolitical choke points, the thermodynamic wall, and finally, future frontiers.
Section 1, Nanoscale Foundations of Compute. Let's begin by defining the absolute structural bedrock of modern AI. Okay, first things first, we've got to completely dismantle this illusion that AI just exists purely in some formless cloud. It absolutely doesn't. Compute is fundamentally bound by physical engineering and real-world thermodynamics. It's the tangible infrastructure, the processing units, the memory bandwidth, those incredibly intricate interconnects that actually executes the billions of mathematical operations required for AI to even function. And to pull off those operations, we rely on a highly specialized division of labor. Think of it like a finely tuned orchestra. You have your CPUs, the sequential masters like AMD EPY or Intel Xeon chips, and they manage the overall execution pipelines and data preprocessing. Then you have the GPUs, which are these massive parallel workhorses explicitly optimized for dense matrix math. And finally, TPUs, which are hyper-specialized ASICs custom-built just to maximize tensor operations. To prevent what engineers actually call GPU starvation, which is where your incredibly powerful parallel accelerators are just sitting there idle waiting for data, we have to maintain this delicate symbiotic relationship between all these components.
Section 2. AI's hardware symbiosis. To really grasp why models with hundreds of billions of parameters demand this specialized hardware, we need to look at how they actually generate text. This brilliantly illustrates the main structural bottleneck of large language models. Notice the 2 distinct phases of transformer inference here. On the left side, we've got the prefill phase. This processes the entire input sequence all at once, so it's highly parallel and compute-bound. But then, look at the right side. That's the autoregressive decode phase, which generates your output tokens sequentially, just one by one. This phase creates a massive memory wall. Why? Because for every single token it spits out, the system has to constantly reload the entire model's weights and the key value cache right back from memory. The bottleneck isn't actually the math. It's just moving the data around. Section 3, Advanced Packaging and Nanoscale Engineering. So, to overcome this memory wall and keep Moore's Law alive, the industry leans heavily on extreme nanoscale manufacturing. 380 million euros. That staggering figure is the cost of just one single high-NA extreme ultraviolet lithography system from ASML. Just to give you a sense of the sheer physical engineering happening here, this machine has over 100,000 components inside it. It literally works by vaporizing 50 micrometer molten tin droplets with a high-powered laser, striking them 50,000 times per second to create a plasma that emits light at exactly 13.5 nanometers. That mind-bending process is exactly what it takes to print sub-7 nanometer features on modern AI silicon. But here's the catch. Even with those incredible lasers, lithography tools run into a hard physical boundary known as the reticle limit. You literally cannot print a chip larger than roughly 858 square millimeters. So foundries like TSMC are essentially forced to build upwards and outwards. They're using advanced 2.5 and 3D packaging technologies, like CoWoS, to stitch multiple separate chiplets together with vertically stacked high-bandwidth memory. Basically, advanced packaging is now displacing lithography as the main driver of performance gains. Now, obviously, software optimizations are just as crucial for navigating these hardware constraints. To actually fit these massive models into limited high-bandwidth memory during training, engineers have to get creative. They use rematerialization, basically discarding and recalculating data on the fly to save precious space. They use activation offloading to temporarily park data over in the slower host system RAM, or they'll leverage parameter-efficient fine-tuning techniques like LoRa, which drastically shrinks the memory footprint of gradient states. It's this constant, intricate dance between software limits and the physical silicon itself. Section 4, Monopolistic Supply Chains and Geopolitical Choke Points. This atomic-scale complexity hasn't just changed tech, it has created some incredibly asymmetric dependencies in the global supply chain. Let's map this physical reality directly onto the global economy.
The Dutch firm ASML maintains an absolute 100% monopoly on the EUV lithography machines required to manufacture the leading-edge silicon powering frontier AI. There isn't an alternative vendor. If any company on Earth wants to manufacture chips below the 7-nanometer node, they absolutely must pass through ASML's technology.
And we see a very similar story with Taiwan Semiconductor Manufacturing Company, or TSMC. They hold an extreme concentration of the world's advanced node manufacturing capacity. We're talking over 90% of the world's most advanced processors, and their fabs are running at near maximum capacity. So this creates a highly centralized global node that is frankly exceptionally vulnerable to regional, environmental, or geopolitical disruptions.
This extreme centralization has naturally prompted some very rapid structural policy shifts globally. On one hand, you have the U.S. CHIPS Act subsidizing domestic fabrication, which includes a recently finalized $7.86 billion award to Intel. You also have proposed allied export controls, like the Match Act, aimed at restricting lithography equipment sales. And then, in direct response, you have China's 15th Five-Year Plan. That's a massive structural push to achieve independent 5 and 7 nanometer class manufacturing through localized foundries like CIMIC, utilizing sophisticated multi-patterning on older equipment. So, objectively speaking, the global supply chain is bifurcating right before our eyes.
Section 5. The thermodynamic wall. Because moving beyond supply chains, we are facing absolute planetary and physical limits. While transistor counts have successfully scaled into the tens of billions per chip, we are hitting a literal wall. Decades ago, back in the 2000s, power density constraints forced a hard plateau in CPU clock speeds. Today, in the 2020s, that memory wall we talked about is aggressively throttling AI GPUs. And as we look toward the 2030s, we're approaching the fundamental CMOS energy floor of roughly 100 femtojoules per operation. We literally cannot make standard silicon much more efficient than that. Look at this projection. It really underscores the core architectural crisis of the von Neumann architecture. In this standard design, memory and processing are kept in completely separate physical locations. Just the act of moving data back and forth between the memory and the processors is threatening to consume an unsustainable fraction of all generated energy on Earth, approaching 10 to the 20th power joules per year by 2035.
To put that into a perspective we can actually relate to, a single query on an advanced generative AI model requires an estimated 2.9 watt-hours of electricity. That is nearly 10 times the power of a standard conventional search. Because AI relies on these massive parallel clusters of GPUs, drawing gigawatts of power, the exponential growth of software models is colliding violently with real-world thermodynamic constraints.
Section 6. Future frontiers of compute. To bypass these thermodynamic limitations, researchers are being forced to engineer completely new paradigms of computation.
You can clearly see the structural contrast here, which points to exactly where we're heading. On the left is the classical von Neumann architecture we've been using, separating volatile memory from the processor cores. But on the right, that's a 3D neuromorphic compute-in-memory architecture. Unlike classical setups, neuromorphic designs integrate the compute logic directly into the memory fabric itself. By actually computing where the data already lives, we can drastically slash the energy wasted on just moving data around. This breakdown really highlights the efficiency gap. Classical computing is clock-driven and relies on volatile memory that constantly needs a flow of power just to retain its data. Neuromorphic computing, on the other hand, mimics the human brain. It uses what's called asynchronous spiking, meaning it only processes data when a specific event triggers it, and it uses non-volatile memory that holds its state without needing continuous power. By copying the brain's sparsity, these chips can process highly complex models at a fraction of the energy cost, scaling linearly instead of exponentially. At the exact same time, the industry is aggressively pushing other hardware innovations. We're seeing processing near-memory configurations, as well as high-bandwidth flash aimed at vastly increasing capacity. But what's particularly wild is TSMC's integration of silicon photonics, known as COPE. This tech actually uses light instead of electricity for chip-to-chip communication. That promises to radically cut data center latency and improve power efficiency by a factor of 2.5. It's a total game changer. So as we look to the horizon, it's clear the ultimate boundary for artificial intelligence isn't just going to be written in code. It's going to be firmly dictated by the physics of materials, the fragility of highly centralized supply chains, and the fundamental laws of thermodynamics. The question I want to leave you with from this briefing is this: what happens when the exponential curve of AI software violently collides with the finite thermodynamic limits of physical silicon? Thanks for exploring the foundations of AI with me today. See you next time.